version of that where we take into account electron redox potential is delta G equals negative NFE, or epsilon, sorry, where epsilon is the reduction potential, F is Faraday's constant, and then N is usually the number of electrons transferred in the reaction. Epsilon is a very hard term when you hear the word reduction potential. And so I like to remember it as the likelihood of being reduced or gaining electrons. So that being said, if we want delta G to be negative for something to be spontaneous, then the, I guess, epsilon net of a reaction must be positive. And so you're gonna have to switch your kind of mentality here if you want delta G to always be negative. And when you're speaking in terms of redox potential, then that means you want it to be positive. And so electrons go from low epsilon to high epsilon is the spontaneous route. So this is a review of 5.11.1, and I know that might be traumatizing for some people, but it actually just shows up in an exam as a quick math problem. So hopefully you don't be like me and ignore this stuff and then all of a sudden have to remember 5.11.1 in the middle of the final. So hopefully you remember how to do these reactions. And so whenever we're doing this type of reaction, we try to look at it from a couple of steps. So let's start to look at this example first, where we have two reactions, and we want to see what would we say is the spontaneous reaction formed when we have two elements like this, like copper and zinc. So when we look at this, they're usually presented as a reduction, where the electrons are on the reactant side, and the copper is reduced to copper, and then the zinc 2+ is reduced to zinc. And then they show you the reduction potential. So what your first goal is that I want to be able to add these two chemical equations such that the electrons cancel out, because we can't really say that I have electrons in my balanced equation. And I want to make sure that my E total is positive. I want my E total to be positive because that is our condition for spontaneity. And so the most logical thing to do then is to flip this second equation and have zinc on the left, zinc 2+ plus 2 electrons on the right. And so that's what we do here. We keep this first equation. We keep the first equation, and then we flip the second equation. And so now that we have this, we can add the two equations together. So that should cancel out the 2 electrons. And so what you get as a final reaction is copper 2+ plus zinc gives you copper plus zinc 2+. And in order to figure out the net epsilon of the reaction, we just add the two values. And note that because we kept the first one okay, we just copy paste the electron reduction potential. But because we flipped the bottom equation, we had to flip that value to positive this time. And so then we add these two together to form plus 0.1101 volts. And one thing you should note is that this is positive, and so this is a spontaneous reaction. One thing people forget, if you ever have to multiply something in this equation, so for example, that the copper wasn't balanced and you had to, let's say, multiply the whole equation by 3. Not applicable for this scenario, but let's just say you do. Make sure that you don't multiply the redox potential. You do not multiply this. Even though you do it for delta G, you do not do it for the epsilon. The epsilon stays the same, regardless if you multiply the equation by a factor in order to create a balanced equation. So make sure you do not multiply the epsilon. So why did we talk about this? And the whole point is that this shows you that electrons moving from one place to another is a spontaneous process, can be a spontaneous process. And so you should think of this as electrons moving from one place to another can be a source of energy release. So this spontaneity definition here tells us that when electrons move from zinc to copper, that energy is released. And so that's how we should interpret this biochemically. And so this is actually what we're going to try to explain in the electron transfer chain, because electrons are basically being moved from one place to another. And in each step, we release energy, and we use that energy for a special process. But usually there is a question in the exam that will involve these electron reduction potentials. So make sure you understand how to add them and how to make the reaction happen. It'll likely not involve copper or zinc because this is not a chemistry class, but it will likely involve enzymes. So this might be replaced as, this could be replaced as NAD plus 2 electrons gives me NADH. It might end up looking like that. So make sure you understand what, how to do the arithmetic for these types of problems. So that being said, let's look right into here. So here is a diagram of the electron transfer chain. And before, we kind of just told you there's proteins and we transfer electrons and then we pump protons. So that is the stuff that you remember from intro bio, hopefully. And we're gonna start with that because hopefully that will connect with you best. So essentially, there are 2 electron sources that we picked up from the TCA cycle and from other cycles we've learned, NADH and FADH2. So all of these electrons from these carriers are going to be dumped into the TCA cycle, sorry, not TCA cycle, electron transfer chain. And what those things are going to do is the electrons are basically going to be passed on from protein to protein until oxygen picks it up and it becomes water. So from a chemical point of view, that's the first thing we want to focus, is that electrons are given to the proteins and then given to oxygen to become water. The next thing is that as the electrons are shifted from one protein to another, they essentially go from high energy to low energy. And so as a result, we should assume that energy is being released. And that energy being released is used by the cell by having protons, or H+, pumped from the matrix to the intermembrane space. And so, as you might think, the consumption of NADH pumps more and more H pluses to the intermembrane space, and it creates a gradient, an electrochemical gradient in the intermembrane space. And then lastly, that gradient will flow down back to the matrix, and that is taken advantage by the ATP synthase, because that flow downward will power the production from turning ADP back into ATP. And so that's an introduction to that process. So hopefully you kind of remember something about that. But the whole point of these NADH and FADH2s, hopefully, is to bring it to oxygen and to pump protons. And the pumping protons, again, is to form ATP. There is a table of the reactions. So what I hope you see from this process is that the transfer of electrons from NAD, giving the electrons to NAD to form NADH, aka the reduction of NAD, is negative epsilon. So that should tell you it's a non-spontaneous process. So it's not surprising that this process is coupled with our energy releasing pathways, glycolysis, TCA cycle. And then additionally, the reverse. If we give these electrons to O2 to form H2O, you see that the epsilon is a very positive number, which means a lot of energy is released. And this is the energy that we use to pump protons to the intermembrane space. And one thing I want to note is, in the past, we kind of didn't talk about each enzyme, but for the sake of this class, we're actually going to. It's a lot of facts, but what's important for you to understand is hopefully why is each step done. The specifics of how many protons it pumps, what the reaction involves, you can write down in your cheat sheet. But what's important for me to teach you is for you to understand why stuff happens in the first place. So one thing to note before we start talking about these proteins is that they share one thing in common. They have what's called electron carriers inside. So basically, an electron carrier is something that has a form that doesn't have electrons, or at least doesn't carry electrons. Then it can take electrons and become reduced, and then it can pass on that electrons to another person or another protein in the pathway. So another example of that is, for example, these iron sulfur clusters. Basically, they're located in an enzyme, and it's this complex of amino acids in the protein itself with the sulfurs from a cysteine with an iron. And so you guys remember, hopefully, that iron can interchange between an Fe2 plus and Fe3 plus form. And so these iron sulfur clusters are known to be electron carriers because these irons can take an electron from the outside, from some enzyme or some carrier, become reduced, and then pass on the electrons to another enzyme afterwards. So these are good electron carriers. NAD and FADH2, you guys have already seen, are good examples of that. If you remember your pyruvate decarboxylase, and if you remember your succinyl-CoA alpha-ketoglutarate decarboxylase as well, those use FADH2 as an electron carrier. Here is an example of a heme. You kind of remember it from Yaffe's half, but not in this function. But heme in cytochromes have the iron present, and they are very helpful in holding electrons and being carriers of them. And then lastly, the ones that you haven't seen before is Q and FMN. These are compounds that can hold on to electrons. So to kind of show you an example, if you look at this form of FMN that is so-called oxidized because it doesn't have electrons, we have the structure in the middle where it's basically nitrogens in a double bond. But once it gets the electrons and becomes reduced, then we start getting amines. And so these are the reduced forms. So hopefully you don't have to think of it as just like a metal changing charge. It can also be an organic molecule that goes from like a more oxidized conformation to now a more reduced conformation. Ubiquinone does the same thing. We have two carbonyls in the oxidized form, but once we get two electrons and get it reduced, it becomes OH and OH. So hopefully you guys can see the oxidation. I would recommend to write these on your cheat sheet just so you know what changes might happen, but you should remember it from the top of your head as these are all carriers of electrons and they help us move electrons around. All right, so let's talk about complex 1 and 2. So the first thing that happens is we have to free the electrons from the NADH. And so what complex 1 will do is take the electrons from NADH so that we replenish the NAD positive. And this is one of the main reasons why the electron transport chain is important. It helps recover NAD positive. Now, that's the end of the story if in terms we're talking about glycolysis and TCA, but what actually happens to the electrons after they drop them off? The only thing that you should really think about is what's the order of passing down the electrons. So the electrons go from NADH to FMN, the compound we talked about earlier. And then FMN gives it to an iron sulfur cluster. And then it gives it to a special molecule called N2. You don't necessarily need to know what that is. It's an electron carrier. And then lastly, it gives it to Q, ubiquinone, to become QH2. And so hopefully these FES, QH2, FMN, you guys can refer back to this page. So QH2 is ubiquinol. And what's more important to note about this is that the